Hello, this is Math Jazz from Almost Cool, and my students are taking an exam tomorrow, and they've written out a bunch of questions that they uh, pulled from the sections for the exam that they're going to have. And so I was just planning on doing solutions to these questions. I've typed them all up, and I'll just show you these one at a time and answer them. So, and if you have any questions that you'd like to ask about calculus, you can feel free to email me at mathjazz, at mathjazz9@gmail.com. The email address is in the description of the video, and or you can type them into chat, and that will work as well. Anyway, so here we have our first problem. Find the limit. We have the limit is x goes to 3 of x squared minus 2x minus 3 over x minus 3. So let's switch the camera over. I guess before we go on, I'm going to set up some hotkeys so I can switch between the two cameras. Maybe I don't know how to do that. Okay, that's fine. We'll just switch manually. There we go. So here's our limit. We have the limit. Let's get the right tool. Let's make it a little bit thicker. So I bought a tablet to write on so that I can do this. There we go. That's what we want. Let's see. Okay, so we want to solve this limit. Now, this limit actually factors, this fraction factors and cancels really nicely. So I'm going to do this. So x goes to 3 of x plus 1 times x minus 3 over x minus 3. And this will cancel, and the limit will be 4. However, we can also test out L'Hopital's rule with this. So notice that as x goes to 3, we get 9 minus 6 minus 3 is 0 on the top, and 3 minus 3 is 0 on the bottom, and that gives us 0 over 0, which is indeterminate, and it's in the form that L'Hopital's rule can work with. So we can take the derivative of the top and bottom. We get 2x minus 2 is the derivative of the top. We have 1 on the bottom. As x goes to 3, we get 2 times 3 is 6, minus 2, and the top is 4. On the bottom is 1. 4 divided by 1 is 4. So both L'Hopital's rule and the factoring and canceling seem to work nicely on this. Okay, so second problem. So we have the limit as x goes to pi from the left of sine x over 1 plus cosine x. So, oops. So we'll swap cameras again. There we go. And okay, so the limit, it's not, limit x goes to pi from the right of sine x over 1 plus cosine x. Okay, so if we plug in pi, we get sine of pi is 0. We get 1 plus cosine of pi. Cosine of pi is -1. 1 plus -1 is 0. So we get something that L'Hopital's rule works on. So that'll be our tool here. The limit as x goes to pi from the right of the derivative of sine is cosine. The derivative of 1 is 0. Derivative of cosine is negative sine. This is the cotangent graph. So if we remember that cotangent has an asymptote at pi and goes down like this. This is our cotangent graph. So this is what I'd like to call finding the limit by graph. Notice that if we're coming from the right side, we're starting here and we're going up to positive infinity. So this limit is equal to infinity. Okay. So let's move on to our next problem. This is another limit problem. I'm just going to write the limit over here. So we have the limit as x goes to 0 of x squared plus 2x plus 1 raised to the 1 over x squared power. So this one here, we're going to let this limit equal L, because we're going to have to take the natural log of this limit here, L equals this. So the natural log of L is equal to the limit as x goes to 0 of 1 over x squared times the natural log of x squared plus 2x plus 1. So this limit here, well, we get 0 plus 0 plus 1. ln of 1 is 0 in the numerator, and we get 0 in the denominator, so we can use L'Hopital's rule. So we get the limit as x goes to 0 of 2x plus 2 over x squared plus 2x plus 1. This is the derivative of the natural log. And then we divide it by the derivative of x squared, which is 2x. And now when we plug in 0, we get 2 on the top, and we get 0 on the bottom. So this is infinite. We have to figure out, is this thing positive or negative? So, well, we'll get a positive 2 on the top. This, this is fascinating. So, as we come from the right, so positive x value is going down to 0, this is positive, and this thing here will also be positive. If we plug in negative numbers, however, then this one is negative. So I mean negative x values going up until we hit 0. We'll have this one is negative. This one's still positive because it's still approaching 2. And we have to figure out what is this doing. So let's figure out where this thing has roots, so we can figure out where this thing is negative and where it is positive. So negative b plus or minus square root of b squared minus 4ac over 2a. And that equals, well, 4 minus 4 is 0, so we get 2 plus or minus 0, so we get negative 1 is our root. Let's check that. Get 1 minus 2. Oh yeah, this is obviously x plus 1 squared, now that I look at it. Okay, so this thing here has one root, and it's at negative 1, and this thing is positive everywhere else. So that means that as we're coming up to 0 from our negative side, this is negative, this is positive, and this is positive. So this here, actually, this limit doesn't exist, because this thing goes to infinity, but from this side it goes down to negative infinity. From this side it goes up to positive infinity. So this limit doesn't exist. Okay, but, however, if we did say that this came from the left, like this, now this limit goes down to negative infinity. So that means that, okay, so that would mean that our limit here is negative infinity, and that means that the natural log of L equals negative infinity, so that means L equals e to the negative infinity, which equals 0. So this would give us a limit that exists. On the other hand, if we had a positive infinity, going from the right, then this would be a positive infinity, which would mean that the natural log of L is infinity, which means that L equals e to the infinity, which is going to be infinite. So that's how you'd handle both of those cases, even though the two-sided limit doesn't exist on this. Okay, let's go to a new problem. Find the derivative of e to the x squared plus x. So this is a chain rule problem. Chain rule is part of the test for tomorrow. So the outside function is e to the x. The inside function is x squared plus x. The derivative of e to the x is e to the x. The derivative of x squared plus x is 2x plus 1. So we take this function and plug this one into it, and then multiply by this function. The derivative becomes e to the x squared plus x times 2x plus 1. Like so. So that one was nice. Okay. Let's look at another problem. Okay, so we'll have to switch cameras for this to show you. Okay. And we'll have to zoom out just a little bit. Okay. So we have here sketch the graph of a function that is continuous and differentiable on -3 to 6 and has the following properties. Maybe zoom out a touch more. An absolute maximum at 6, an absolute minimum at -3, a local minimum or a local maximum at x minus 3, and a local minima and local minima at x equals -2 and x equals 5. Okay, so let's do that. There we go. So let's get some coordinate grid down. The first thing it wanted was an absolute maximum at x equals 6. So let's just draw that here. So there's our absolute maximum. And an absolute minimum at -3. And we want a local maximum at 3. And local minima at 2 and 5. So that seems to work. So we need to come up. Here's our local minima. Oops. My pen is no longer traveling to the other screen. Okay. Oops. I can't quite do this with a mouse. There we go. Okay, so that has the 2 local minima that are required. It is a function, it's continuous, and it's differentiable, and so that satisfies that problem. Okay, so the next one is we're going to find I need to figure out how to get my pen on the right screen. Oh, there we go. Okay. Okay, so the next problem is another chain rule question. So we will do this. We have the derivative of 7 cosine e to the x squared. That's going to equal, well, constants just come out. Okay, so let's make our chart actually. So the outside function is cosine x, its derivative is negative sine x. Derivative, the next function in is going to be e to the x, its derivative is e to the x, and the last function is x squared, its derivative is 2x. So we take this function and we plug this one into this one into that one. So we get negative sine of e to the x squared. Okay, and then we're done with this. We move on to this one. We plug this one into that one. So we get e to the x squared. We're done with that. And then we multiply by this and we're done. Okay, so this is our derivative. Next question. We want to find dy dx for y cubed equals negative x cubed plus 27. So we take the derivative of both sides, getting 3y squared dy dt equals negative 3x squared dx dt plus 0. All right, we're not doing a related rates. We're doing a. If we were doing related rates and the thing we were taking the derivative against was t, this would be right. But we're doing implicit differentiation, so we get dy dx here, and no dx dt there. And now we solve for dy dx, so we get dy dx equals, the 3's cancel, we get negative x squared over y squared. So that's our derivative. Now if we were asked to find the second derivative, we just take the derivative of everything here. So we get d squared y dx squared equals, this is a quotient rule, so we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, and since we take a y derivative there, we need to multiply by dy dx, and then we square the denominator. And that is usually not accepted as an answer. We have to get rid of the dy dx, so we have to substitute this in. So we have y squared, or negative 2x y squared, negative 2x y squared plus x 2x squared y times negative x squared over y squared all over y to the 4th. And this is a fine answer. And we could cancel some things, but it's fine. Okay, so let's move on to the next question. This one is another limit question. We have the limit as x goes to 0 of e to the x minus 1 times cosecant x. Well, cosecant has an asymptote, it goes up to infinity, and e to the x minus 1 goes to 0, so this is a 0 times infinity indeterminate expression. So we're going to have to rewrite this. I usually flip trig functions upside down, although if it doesn't help, then I'll go back and do it the other way. E to the x minus 1 over sine x. This goes to 0, that goes to 0, so now it's in the right form. We can use L'Hopital's rule. We get the limit as x goes to 0 of e to the x over cosine x. And when we plug in 0, we get 1 over 1, which is 1. Okay, so that's the limit there. That's actually pretty cool. The trig function and e to the x have this nice limit here. So we'll move on to the next question. So we have the limit as x goes to 0 of arctangent of x over the natural log of x plus 1. So if we plug in 0, we get arctangent of 0, which arctangent of 0 is 0. And when we plug in 0 here, we get natural log of 1, which is also 0. So we can take the derivative with the limit as x goes to 0 of derivative of arctangent is 1 over x squared plus 1. Derivative of the natural log is going to be, well, the derivative of the inside here is 1 divided by the function itself, so we get x plus 1 in the numerator. And when we plug in 0, we now get 1 over 1, which is 1, and that'll be our limit. Okay. So the next one is show that f satisfies the hypotheses of Rolle's theorem and find all points x equals c that satisfy the conclusion of Rolle's theorem. Okay, so the first part is show that our function satisfies Rolle's theorem. So the thing that we need to know now is, well, what is Rolle's theorem? So Rolle's theorem is if f is differentiable on an open interval a to b and continuous on the closed interval a to b, And our last hypothesis is if f of A equals f of B, then there exists C in between A and B, so this is in the interval A to B, such that f prime of C is equal to 0. Okay, so that is Rolle's theorem. The hypotheses of Rolle's theorem are differentiable on an open interval, closed on the closed interval, with the same endpoints, and the endpoints have the same y values when plugged into f. So let's check that. F is equal to x cubed minus 2x squared minus 4x plus 2, and the interval we were asked to look at is -2 to 2. Well, polynomials are differentiable and continuous everywhere, so that satisfies this one, and then we just have to show that f of A equals f of B. F of -2 equals -2 cubed minus 2 times -2 squared minus 4 times -2 plus 2, which equals -8 minus 8 plus 8 plus 2 equals, looks like -6 to me. And then f of 2 is equal to 2 cubed minus 2 times 2 squared minus 4 times 2 plus 2 equals 8 minus 8 minus 8 plus 2, which also equals -6. So this satisfies all three hypotheses of Rolle's theorem. So that part is done. And then the next part is to show, or to find the point C that satisfy the conclusion. So all we have to do is figure out where does the derivative equal 0, because derivative equaling 0 is the conclusion, and then any point C that makes that happen satisfies the conclusion. So f prime of x is equal to 3x squared minus 4x minus 4, and then we want to factor this. Do we just want to plug this into the quadratic formula? -b plus or minus the square root of b squared minus 4ac. All over 2a. Well, this is 4 plus or minus, so we get 4 times 3 is 12, times 4 again is 48, the two negatives cancel, 48 plus 16 is 64, square root of 64 is 8 over 6, so we get, looks like 4 plus 8 over 6 is 2, and 4 minus 8 over 6 is negative 4/3. Right, 4 minus 8 is 4 divided by 6 is negative 2/3. There we go. Okay, so which of these satisfy the conclusion? Well, the conclusion is that there's a C in the open interval, so not including the endpoints. 2 is an endpoint, so it doesn't count actually. This is the only one that counts, because that is in the interval. Okay, so that was a fun question. We have, let's see, find the limit. We have the limit as x goes to 3 of x minus 3 over x squared minus 9. Okay, so with this one we can cancel out common terms, or we can use L'Hopital's rule. I'm going to choose to cancel out the x minus 3 from the top and bottom. And then because L'Hopital's rule is on the test, I'll do it the other way as well. limit as x goes to 3 of, take the derivative. So we get 1 on the top, we get 2x on the bottom. We plug in 3, we get 1 over 2 times 3 is 6. So that works both ways. Okay, and we're asked to find the derivative of f, where we have f is equal to cosine of 2x plus 1. This is a chain rule, so f prime of x equals the derivative of the outside function is negative sine, the inside function is 2x plus 1, and the derivative of the inside function is 2. So this is our derivative. Okay. Here's one. Show that 2x plus cosine x equals 0 has exactly one solution. So the first part of this is show that we have a solution. Okay, so we're going to use the intermediate value theorem for this. So let f of x equal 2x plus cosine x. F of, let's say, negative 10 is equal to negative 20 plus cosine of negative 10. Well, cosine is never bigger than 1, so this is definitely going to be less than or equal to negative 20 plus 1, which is less than 0. And then f of 10 is equal to 20 plus cosine of 10. And cosine is never smaller than negative 1, so this is going to be less than or equal to positive 19. Sorry, it's going to be greater than or equal to positive 19, which is greater than 0. Also, f is continuous on negative 10 to 10. So, by the intermediate value theorem, there exists c such that f of c equals 0. Well, what does it mean for f of c to equal 0? That means that 0 equals 2c plus cosine c. And that's a solution. That means c is a point that makes this a true equation up here. Okay, so that proves that there is a solution. Now we need to show that there cannot be two. Now, proving that there can't be two is the same as proving there can't be three, can't be four. Because if you have three solutions, then you obviously have two of them somewhere, right? If you have three, then you have at least two. So if we show that there can't be two of them, then there's no way you can get all the way to three of them or more. So we're going to assume, this is a proof by contradiction, there are two roots, A and B. F is continuous and differentiable everywhere. So, mean value theorem applies. What does that say? Well, it says that there is a C such that f prime of C is equal to f of B minus f of A over B minus A. But f of B is 0, f of A is 0, 0 minus 0 is 0, and we just said that B and A are two different numbers, so 0 divided by something that isn't 0 is 0. Well, that means that the derivative has to equal 0 at C. So let's take the derivative. We get 2 plus negative sine. So 2 minus sine, plug in c, is equal to 0. There you go. Well, if 2 minus sine c equals 0, that means that sine of c equals 2. That's a problem. Sine is never bigger than 1. This is a contradiction. Now, when we get a contradiction, that means that the last assumption we made had to have been false. Okay, so we go up, and what's the last assumption we made? Well, the only assumption we made is that there are 2 roots. So that's false. So if there can't be 2 roots, that means that at most there's 1. But we already showed that there is 1, so that means at least there's 1. So that means that there's exactly 1. And that proves the problem. Okay. We're asked to find the critical points of f of x equals 6x cubed plus 9x squared minus 12. Critical points are places where the derivative is undefined or 0, so we find the derivative. Get 18x squared plus 18x. And we want to figure out where this is 0. Well, it's equal to 0 when x is equal to 0, because if I plug in 0, I get 0 plus 0. Or when x is equal to negative 1. When I plug in negative 1, I get positive 18 and negative 18. There can't be more than 2 roots because this is a degree 2 polynomial. So here are our critical points. We also, if we don't want to do this by inspection, can factor 18 times x times x plus 1. And this is where a 0 root comes from. That's where our negative 1 root comes from. Okay. So now we have another implicit differentiation question. And then we're done with the first page of problems. So, we want to find dy dx when we have x squared equals x squared plus y squared equals 4x. So when we take our derivative, we get 2x plus 2y y prime equals 4. So we get 2y y prime equals 4 minus x minus 2x. We get y prime equals 4 minus 2x over 2y. So, if we wanted to find the second derivative, we do the same thing as we did before. We use the quotient rule, and then we'll have to substitute in our y prime equation, because we'll get a y prime when we take the derivative of the right side here. Okay, and that's the end of the page. So let's flip the page. Great. Okay, so this one is another limit. We want to find the limit as x goes to 5 of x cubed minus 5x plus 3 over x squared minus 25. Now if we plug in 5, we're going to get 75 minus, we're going to get 125 minus 25 plus 3, so that's 103 on the top, and we get 0 on the bottom, so this limit doesn't exist. But it's good to see these, because sometimes, we blindly apply L'Hopital's rule when it doesn't apply, and then we lose points on our exams. Let's do another limit. As x goes to infinity of the natural log of x squared plus 2 over the square root of x. Now as x goes to infinity, we get natural log of infinity, which is infinity, over square root of infinity, which is infinity. So this is something that L'Hopital's rule works on. We get the limit as x goes to infinity of, we get 2x on the top, we get x squared plus 2 on the bottom, and we get 2 square root x on the top. So the derivative of square root x is 1 over 2 square root of x, but the denominator of a denominator goes to the numerator. Dividing by a fraction is the same as multiplying by the reciprocal. Yeah, so this is our derivative of the top. This is 1 over the derivative of the bottom. And so from here we have a higher power in the top than the bottom, so this is going to go to 0. So yeah, so that's just how these work, is that if you have a larger power in the top than the bottom, it'll go to infinity. If you have equal powers, you divide the coefficients, and if you have a higher power in the bottom, it goes to 0. Okay. Now we have another chain rule question. We want to find the derivative of tangent of cosine sine of x. The outside function's derivative is secant squared. Plug in our inside stuff, cosine of sine of x. We take the derivative of the next thing, which is negative sine, plug in our inside function, which is sine x, and then we multiply by the derivative of the inside function, cosine x. So this is derivative of tangent, didn't change anything inside. Derivative of cosine, didn't change what was inside. And derivative of the inside thing. So that's our derivative. Next problem. This is problem number 19 on the paper. So we have find the local maxima and minima of f of x equals x times x minus 5 cubed. So we first need to find the derivative. So we get f prime of x equals product rule, chain rule is fine here. X minus 5 cubed. So the derivative of the first is 1 times the second, plus the first times the derivative of the second, times the derivative of the inside, which is 1. So this is our derivative. Let's factor out x minus 5 squared. So we have x minus 5 squared. We leave behind 1 x minus 5. And then we factor out x minus 5 squared, and we're left with just a 3x here. So we get x minus 5 squared times, looks like 4x minus 5. So that means that our roots are going to be x equals 5 and x equals 5/4. These are our critical points because they are the zeros of our derivative. We have no asymptotes on our derivative. We have no, it's defined at every point, so we only have to worry about where it is 0. Okay. Let's do the next one. We want to find the derivative of arctangent. Well, that means that x equals the tangent of y, which means that the derivative equals 1. Derivative of x is 1. Derivative of tangent y is going to be secant squared y times y prime. So y prime equals cosine squared y. We draw a triangle. If this is the angle y, well, tangent of y equals x, so that means that the opposite divided by the adjacent has to equal x. So we just pick x and 1. We could pick 2x and 2 and 10x and 10. Whatever makes the quotient, of this side with this side equal to x. Now, this is the easiest way to do it. we want the cosine of y. Cosine is the adjacent over the hypotenuse, so we find the hypotenuse is x squared plus 1, the square root sign. So this is the hypotenuse. 1 over this is cosine, so 1 over the square of this is cosine squared. So we get 1 over x squared plus 1 is our derivative. This is the proof that the derivative of arctangent is 1 over x squared plus 1. Okay, now we want to find the derivative of f of x equals x to the sine x. So the first thing I want to do is take the natural log of both sides. Now we take the derivative, we get f prime of x over f of x equals derivative of sine is cosine x times natural log of x plus derivative of natural log of x is 1 over x, so we get sine x over x. And now to find f prime of x, we just multiply both sides by f, but f equals that, so we get cosine x natural log of x plus sine x over x times x to the sine x. This is our derivative. Okay, so here is another derivative, f of x equals 4x natural log of 7x minus 4x. We want to take this derivative, it's a product rule, so f prime of x equals derivative of 4x is 4 times the natural log of 7x plus 4x times the derivative of natural log of 7x, so we get a 7 in the top because that's the derivative of 7x, so we get a 7x in the bottom because that's the argument of natural log, and then minus 4 is the derivative of 4x. This is our derivative. Okay. So now we have another implicit value problem. We have 7x squared minus y squared equals 5. We want to find dy dx, so we get 14x minus 2y y prime equals 0. Y prime equals 14x over 2y. The negative here cancels with the negative we get when we move the 14 over. We can actually cancel these and get a 7x over y. That's not too bad. Okay, let's do the next one. We have the limit as x goes to 0 of cosine x minus 1 over sine squared x. Well, let's take a derivative. We get negative sine, the limit as x goes to 0 of sine x negative over 2 sine x cosine x. The signs cancel. And we get negative 1 over 2 times 1, which is negative 1/2. The next couple are brutal. You guys, picked some hard ones. So we're going to do some chain rule questions, and they're not particularly pretty. We have sine squared of the square root of x squared plus x plus 1, and cosine squared of the square root of x cosine x. Okay, let's do this one first. The outside function is x, well, the outside function is x squared, so we get 2 sine of the square root of x squared plus x plus 1. Then we go in one step, we get derivative of sine is cosine of the square root of x squared plus x plus 1. And then we go in another step, derivative of the square root is going to be 1 over 2 times the square root of x squared plus x plus 1. We go in one more step, and the derivative of that polynomial is 2x plus 1. This is the derivative of our first problem. Now we want to take the derivative of this. So we get 2 cosine of the square root of x cosine x. We go in one step, we get negative sine of the square root of x cosine x. We go in one more step, we get 1 over 2 times the square root of x cosine x. We go in one more step, we get a product rule. So we get cosine of x, because that's the derivative of the first times the second, so 1 times cosine, plus x times the derivative of cosine, which is negative sine x. So that's the negative, here's the sine. And then we've gone all the way in. So this here is the derivative of our second problem up here. Okay. Let's go in one more derivative, and then we have something else. So we have the derivative of the square root of e to the 2x. Okay, so this is e to the 2x to the 1/2, right? And taking something to an exponent and then raising it to an exponent, you can just multiply the exponents. So this half cancels with that x. The derivative of e to the x is e to the x. And this is not what the student tried to do. But let's show that it works even if we didn't recognize that. Oh yeah, so here's our function, and then the derivative equals e to the x. Let's try taking the derivative of this. So we get 1 over 2 times the square root of e to the 2x. That's the derivative of our square root function, and we plug in all the inside stuff. And then the next thing, we get e to the 2x, because the derivative of e to the x is e to the x, and we plug in our 2x, it's there. And then we multiply by the derivative of 2x, which is 2. So that 2 cancels with that 2. And we have the square root of something and the thing on top. So whenever you have a over the square root of a, that's equal to square root of a squared over the square root of a, and it cancels to be just the square root of a. So we have this thing in the numerator and its square root in the denominator, so that's just going to be square root e to the 2x, right? And well, so you know this thing is exactly what we started with, but this is also the derivative. We did the chain rule. There are only two functions that are their own derivative, and those are e to the x and 0. So either this is 0 or it equals e to the x, and I can tell you this isn't 0 because if we plugged in 0, we get e to the 2 times 0 is e to the 0 is 1, square root of 1 is 1. So when we plug in the point 0, we get out a value of 1, but if this were the 0 function, when we plug in anything, we should get out 0. So it's not the 0 function. That means it must be e to the x. So if we didn't figure out how to manipulate the exponents to get that, it still comes out. Okay. So we have oil spilling in a perfect circle on top of the ocean. The oil is, I don't know if I can draw a boat. There's a boat. That boat is spilling oil in a circular pattern on the ocean. What we know is that, here's it again, the radius is increasing at 3 feet per second, so du radius dt equals 3. And we want to find the way that the area is changing. So we know that area equals pi r squared, so dA dt equals 2 pi r dr dt. The radius, we're told, is 12 feet in the problem, so we get 24 pi times dr dt, which is 3. That's our dA dt. 3 times 24 is 72 pi. This is how our area is changing. 72 pi per second. Wow, 3 feet a second. I guess oil flows pretty quick, so that might be reasonable. Since our radius is in feet, the area is in feet squared, so this is a feet squared per second. That's what we got. Okay. Ooh, last problem. Okay, so with this one, we have a ladder. Okay, here is we have a 10-foot ladder that is 6 feet from, or the base is 6 feet from the wall. So this side is 6, this side is 10. We want to figure out what is the rate of change of this angle here. We're told that the base is moving at a rate of 1 foot per minute, so we'll say dx dt equals 1. We'll call this side x. At the time we're interested, x is 6, and we want this angle, which we'll call theta. The ladder is not changing length, so what we know is that, let's see, this is the adjacent, that's the hypotenuse, so cosine of theta is equal to the adjacent over the hypotenuse. We take our derivative, we get negative sine theta d theta dt. Is equal to 1/10 dx dt. This is what we're looking for. Now, sine of this is going to be the opposite over the adjacent, and we're looking at the time when x is 6, so this is a 6 and that's a 10, then this is an 8, because this is a 3, 4, 5 triangle, or we can plug it into the Pythagorean theorem if we wanted. So sine is going to be 8 over 10, well, negative 8 over 10, so negative 4/5. And this is what we're looking for, d theta dt. And this is 1/10. And dx dt is, well, we were told that it is 1 at this instant. So times 1, so we get d theta dt equals, that 5 cancels with this, and we get, looks like negative 1/8. So this will be in radians. So the angle here is shrinking at that instant at negative 1/8 of a radian per minute. Okay, that is our last problem. It looks like there are no questions on the live stream chat, and it looks like there are no questions on the email. So we will wrap this up now. So thank you for watching. I hope that you all do very well on the exam tomorrow, or I guess it's in the testing center, so you might take it over the weekend or beginning of next week. But whenever you take it, I hope that you do well on it. And everyone else that's watching, I hope that you're enjoying learning calculus, and we will, see you next time. And ask any questions that you want by emailing me, and I will make videos on them. So, bye.